University of Munster in Germany. I've known him since very, very long time. I don't know, when we're probably still postdocs, him in Mainz and me somewhere else at Caltech probably or something. Christian studied in Mainz at the University of Mainz and has worked on a number of projects, including some projects at CERN, but most notably he has actually been pretty much always with the kinematic neutrino mass, first with the famous Mainz experiment, and then he's been in the Katrin experiment, for which he was spokesperson until a few months ago or something. So he's also heavily involved into the xenon dark matter experiment, and so he could have given 2 different colloquia, and I actually gave him instructions to talk about the Katrin experiment and the kinematic neutrino mass, because I think it's more unique, and so it's probably more interesting, whereas, you know, others like Dan can tell us about dark matter searches, you know, locally here. Okay, so I guess without, I don't want to spend more time. Actually, he has also a project on PET scanners and other things, but we're really eager to hear about kinematic neutrino masses today.
Yeah, thank you very thank you very much for the kind introduction and for the invitation. I'm very happy to be here. I visited SLAC yesterday, today here, and really it's such a wonderful place with so great physics and so great physicists. I really enjoyed it. I would like to talk about Katrin today, and after an introduction, I will explain you the experiment and tell you about the recent results. We are going to publish in summer even more results. I will tell you a little bit about the sensitivity, but they are still not public. We are writing up the paper. It's not yet finished. And then I will tell you about improvements and future goals of Katrin. Where do we go before I will conclude? So neutrinos, as you probably well know, are 3 out of the fundamental particles of our standard models, and they have spin and half, they are neutral, they only weakly interact, and that means their interaction length is light years if the neutrinos are of typical scales like reactor or solar neutrinos. So they just go through the Earth. They are the most abundant particles in the universe, together with the photons of the cosmic microwave background. It's about 356 neutrinos per cubic centimeter in total. In the original standard model, which held up to the end of last century, neutrinos were considered massless because with a typical mass generation process with the Higgs particle, you turn a left-handed particle to a right-handed particle, but in the standard model, neutrinos were all left-handed, and therefore you could not do that with the standard Yukawa coupling. And that is why neutrinos were considered only left-handed, because they had no mass up to recently. That are the masses of the fundamental fermions. So you see in the first generation the up and down quark, which makes nucleons, and they together make the nuclei, and the electron make all the atoms here. And they are at least 6 orders of magnitude to the neutrinos, if not much more. And the whole picture changed at 1998, when Kamiokande found that atmospheric muon neutrinos turn in flight into tau neutrinos. That was neutrino oscillation, which is only possible if neutrinos have a mass. A bit later, the Sudbury Neutrino Observatory, SNO, found out the reason for the solar neutrino puzzle, namely that electron neutrino in flight go to muon and tau neutrinos, again only with mass. And these 2 findings were honored with the Nobel Prize in 2015. Just a quick reminder, what is neutrino oscillation? You have 3 flavor states and 3 mass eigenstates, so at least two of them should have a non-zero mass, which are not identically but mixed by a unitary 3×3 matrix, UMPS. And then a neutrino oscillation experiment is a triple slit experiment. You generate a neutrino of a certain flavor, for example, a muon neutrino, which is characterized by the appearance of a muon. You let them propagate through space, and the propagation works with mass eigenstates, which you produce from the muon neutrino according to that mixing matrix. And when you detect them in a certain flavor, and therefore you have to reconcile its flavor composition again by the inverse of that matrix. And because of the propagation, the phases propagate a little bit different because of the different masses. When you put them together, it's not automatically a muon neutrino anymore, and you can get a tau neutrino, for example. Why? If we now know by neutrino oscillations, and that has been confirmed by so many experiments, more than a dozen, with accelerator, reactor, solar, and atmospheric neutrinos, why, if we know that neutrinos have tiny masses, why it's so important to know about what the masses are? There are two reasons. One comes from particle physics. Neutrinos are so much lighter than all the other 9 fermions of the standard model, and therefore it's very unnatural that by having just now a right-handed neutrino to make up the neutrino mass by just the Yukawa coupling to the Higgs. There are other possibilities, like these two Ziso mechanisms, which have new particles in and have new mechanisms to create the masses in a way that the neutrino mass gets much smaller in a natural way. And that is physics beyond the standard model. And we would like to know about that. And on the other hand, I told you there is a cosmic neutrino background released in the very early time of the Big Bang, at the first second. And these neutrinos are so abundant, 1 billion times more abundant than atoms in the universe, that even small mass neutrinos count, and they would have influenced, depending on their mass, the structure formation of the universe. And therefore, for cosmology and astrophysics, it's also very interesting to know. How can you probe the neutrino mass? If that is influencing cosmology, you can turn the argument back and can take cosmology observations to determine the neutrino mass. What you do, you compare power at different scales, and the best what we know is the measurement of the cosmic microwave background radiation, which comes all around from all directions to us, and the little temperature fluctuations in the universe, which you see here as the picture of the Planck calibration, can be decomposed by a multipole analysis in these fantastic peaks, and the ratio of the different peaks tell you what is the matter content and what is all about in the universe, matter and energy. And you put together that with a big scale, the large scale structure from galaxy catalogs, which you measure, for example, by the Sloan Digital Skies Array, knowing the number of neutrinos per cubic centimeter, you put that in a large computer simulation, and you find out that the neutrino mass cannot be bigger than, for example, the sum of the 3 neutrinos and 120 millielectron volt. Of course, that is somewhat model dependent, but a rather general statement. The second way is also pursued here in the group of Church-O'Crata, is searching for the neutrinoless double beta decay. In a neutrinoless double beta decay, you have 2 neutrons which decay in coincidence into 2 protons emitting 2 electrons, and the 2 emitted antineutrinos annihilate virtually and have an inner vertex. This process only works if the neutrino is equal to its antiparticle, and you have, of course, some challenges in the nuclear matrix element, but you would be very sensitive to the lepton number violation, which would be really a big discovery if discovered. You are sensitive to the neutrino mass. Again, you have 3 mass eigenstate. Here is a plot of the minimal neutrino masses, and here you see a coherent neutrino mass at m beta beta, which you are sensitive to, and the two neutrino mass hierarchies, which are still possible, leave you that colored region, and that where the current limits are on a log plot, and here a very recent result from the Majorana demonstrator on a linear scale, and that part here needs to be explored. The third method is really a direct method without assuming some cosmology assumptions and not assuming that you have Majorana neutrinos. Majorana neutrinos are neutrinos which are identical to their antiparticles, which you would not allow for charged particles like the other 9 fundamental fermions, electron and the quarks and muon. But neutrinos could be that, and that could be the key to make them such light with the CISO mechanism, which I have shown on these plots. Now, in the direct neutrino mass determination, you nothing assume than just the energy-momentum relationship and energy-momentum conservation. What you do, you take a weak decay and check for the decay spectrum of the particles which you can measure. And for example, we will see in a second that you can just describe the decay spectrum and check what the mass is. Of course, there is another way to do it if you have a catastrophic cosmic event like a core collapse supernova, which emits on a small time scale a huge bunch of neutrinos. You can do a time of flight measurement. Unfortunately, that doesn't happen too often, a few times per century, and it's very difficult to put all the assumptions about that core collapse explosion into account. So what we are after is to measure the beta decay and the electron energy spectrum. In a beta decay, you emit an electron and an electron antineutrino. You measure the energy of the electron, which is a continuous spectrum because it shares the energy with the neutrino. And then you go to the very upper end of the spectrum where, if you both share the energy, the neutrinos emitted with very little energy, that means non-relativistically, and then it opens to you its nature of the mass. And that is shown here in that enlargement where you see the beta spectrum rises quadratically if the mass is 0 and deviates from that and stops earlier if the mass is non-zero. And it's all about to distinguish these two shapes. And just to give you a flavor how difficult that is, that gray shaded area here corresponds to only 2 times 10 to the minus 13 of all tritium beta decays if the neutrino mass is as big as 1 electron volt. So it's super difficult to measure that, and you need an instrument of ultra high precision. And that is what the Karlsruhe Tritium Neutrino experiment Katrin is about. It's a 70-meter long setup with a molecular tritium source, a differential pumping section, and a doublet of 2 spectrometers and a counting detector. And how that goes, I will explain on the next slides. But I just want to mention a little bit the most challenges is the stability of this dynamic tritium source where you let in tritium gas going in, which streams out to both sides and pump back. And you have to have this dynamic source stable at the per mil level. The spectrometer is put on high voltage. You have to do the energy scale on a ppm level, which is world leading demands. And you need a very low background in the counting device here and ultra high precision everywhere along the setup. This experiment is undertaken at the Karlsruhe Institute of Technology, a national lab and university in Germany, by an international collaboration of about 150 people out of 8 countries from 24 institutions. And you see the happy faces of our recent Katrin collaboration meeting. Here you see the institutions and our fundings. So we have 6 institutions from the US who contribute. This is our molecular tritium source. I told you tritium goes in, freely streams out to both sides and is pumped back again. The whole tritium source is inside a superconducting chain of solenoids. So if tritium decays here in the main beam tube, the electrons are guided towards the spectrometers. The beam tube has a diameter of 9 centimeter and operates at 80 Kelvin in a 2.5 Tesla magnetic field. The inlet flow of 5 times 10 to the 19 molecules is corresponding to a column density which we achieve of 5 times 10 to the 17 molecules per square centimeter, which is about 1 over the inelastic electron tritium cross-section, scattering cross-section. Why do we do that? If we increase column density even more, we would saturate the count rate near the endpoint because the electrons of the decay get lost by inelastic scattering. I think you know that in hydrogen, the first excited state of atomic hydrogen is 10.2 electron volt, 3/4 of the famous 1 Rydberg, and in the molecule it's about the same. So these electrons undergoing 10 electron volt energy loss will be missed. The whole beamline you see here with the fish eye is of course a straight line. And just to tell you a little bit how complex the whole system is, I show you a few pictures. That is our laser Raman spectroscopy setup, which allows you to tell you in 100-second times to a per mil precision what is the tritium content with respect to hydrogen deuterium at the per mil level is. This is a calibration electron source behind. This is part of the cryodifferential pumping section because you need to get rid of 14 orders of magnitude of tritium flow towards the spectrometers. And we do that by differential pumping and cryodifferential pumping. And here's another calibration source. Then there comes a small spectrometer, which we do not use much at the moment, and the big spectrometer, which is put on high voltage. So please don't touch it. It's a 24 meter long, 10 meter size setup, which has 18.6 kilovolt on with a precision of 1 part per million. Of course, there is a fence around with an interlock. Inside, there is a dual layer wire set up, and outside, there's an air coil to compensate the Earth's magnetic field and fine shape the magnetic field here. Both are used for background reduction. I will show you in a second the reason. The whole spectrometer is the largest ultra-high vacuum tank mankind has built, and it runs at a vacuum of 10 to the minus 11 millibar, which is the partial pressure, the pressure you have at the surface of the moon. How does this spectrometer operate? It's a spectrometer of the so-called McE filter type, magnetic adiabatic collimation followed by an electrostatic filter. And it operates on the fact that the magnetic orbital momentum of a particle, which is a non-relativistic limit, the cyclotron energy over a magnetic field is a constant of a motion. If you have an electron grading around a magnetic field line, and if you change the magnetic field, make it, say here, 4 orders of magnitude smaller, the cyclotron energy goes 4 orders of magnitude smaller. Where does this energy go to? It goes to longitudinal energy. So what you do here, you have a gyrating electron with several angles, and they get all paralyzed when they come into the low magnetic field region. And then you let them run against this retarding potential, which you apply to that spectrometer, and all those electrons which have more energy make it to the detector, where the magnetic flux goes back again, because the magnetic strong fields, the solenoids, are at the entrance and the exit. So what you have then is a threshold spectrometer, integrating spectrometer, where the width of that threshold is of the order of an electron volt. We typically run now at 2.6 electron volts. This instrument allows you ultra-precise beta-electron spectroscopy, which is a huge accepted solid angle, because you collect nearly all the forward angle by a magnetic field. And for those who are expert in these kind of things, it's a magnetic field of a magnetic bottle, which is used, for example, for storage of particles. Now it's a perfect instrument what concerns energy resolution and acceptance. But it's a magnetic bottle. It means that electrons, for whatever reason, are born here with little energy, will be electrostatically accelerated and counted at the detector. So you have to avoid any electron generation, and that's why we have 10 to the minus 11 millibar. Any electron generation here in the middle. Okay, we keep that in mind. After that spectrometer, there's a high resolution electron counting detector. It's a backside pixelated silicon pin diode with high energy resolution sitting in an active and passive shield, again in a superconducting solenoid. Now, let's do with that instrument now beta spectroscopy. Here I show you the beta spectrum on a log scale. Near the endpoint is where you should measure the neutrino mass, and to be more precisely, we are sensitive, because it's a phase-based experiment, to m square, because that comes from the relativistic energy-momentum relationship. E square is p square plus m square. In the units of particle physics, speed of light is 1. We determine the background rate above the endpoint of the spectrum, and we determine the signal strength and the endpoint from that shape here. So only 4 fit parameters, where this parameter is sensitive to the neutrino mass, which you see here, it's only at the endpoint by showing 2 beta spectrums, the difference, one for 0 mass and a little small mass. And therefore, that is our measurement point distribution. We concentrate with our measurement point a little bit, a few electron volts below the endpoint. So 4 fitting parameters essential. A rather simple task, if you would say. Now, we have to convolute the theoretical beta spectrum with our response function, which is that step function, the integral response of the spectrometer, which is repeated and smeared out a little bit later because we have inelastic scattering, which is determined by an electron gun and conversion electron measurements I will show you in a second. These 2 spectra are convoluted, a background is added, and that is a blue fitting line which we show to one run of 2 hours of the beta spectrum, which enhance error bars that you can see the error bars, otherwise they would disappear here. Of course, with your fantastic beamer, one would probably see them still. Now, we did this for our first run of 2019, where we got m square, which is a fit parameter, which is not physically constrained. It can run positively and negative by fluctuations of -1 electron plus -1 electron volt squared. You see here the fit with data points with a 50 times enhanced error bar. You would not see the fantastic small error bars of the Katrin experiment, but you can see the residuals, the differences in the standard deviation of the fit to the data, and there is no structure visible. That allows us to give an upper limit of 1.1 electron volt. It's the first result which we achieved in autumn 2019, which made it to the front page of Physical Review Letters. Now, just a year ago, we published our second result with more data, our Science Run 2 in Nature, again the front page. We had a much higher signal rate and a lower background rate, so we could go closer to the endpoint. Again, a good fit to the data. Now, m squared got not negative but positive. That's good, because you would fluctuate in fluctuations. You would see 50% time around 0 if the neutrino mass is small, like cosmology predicts. You would see positive and negative results. The endpoint is an agreement to external measurements with panning traps. That's great. And you get a limit of 0.9 electron volt, combining the 2 of 0.8 electron volts, and you see the 2 likelihood functions, they all agree, and they are close to m squared equals 0. To analyze these results, there is a lot of work going on into the systematics. And I want to just tell you what we are all care about. If you do tritium beta decay, the daughter molecule is an ion, a tritium helium-3 ion, which is excited into vibrations and rotations and electronic excitations, which we get by quantum chemical calculations. The tritium source has 10 to the 11 decays per second. It's magnetically confined, so it's a plasma. It has all the properties of a plasma, and we should control the plasma properties, which depends on the surface conditions and on the rear wall. The magnetic fields need to be known relatively to a per mil level. The detector efficiency needs to be known. We need to know the energy losses by inelastic scattering of electrons, which we calibrate by an electron gun. And the source is dynamic, so you let always tritium flow in, and you take it out by pump. So it has to be stable in count rate dynamically, and the tritium fraction should be constant. And I showed you the laser Raman spectroscopy. And then the background should be constant and stable and small. We describe all that by our systematics description, and we incorporate that into our analysis by 3 different methods: covariance method, Monte Carlo propagation, and the classical pull-term methods. And we describe that all in our recent analysis paper. And just to give you a flavor how we do that systematics, I show you how we measure inelastic electron scattering. We have a pulsed frequency quadrupled laser which pulse photoelectrons in our tritium source, and we have that fantastic spectrometer to measure that. If you do that, you measure a transmission function very sharply, and then you see 1-fold scattering, 2-fold scattering. It's an integral mode, but we can also apply a time of flight measurement because we have a short laser pulse for our photoelectrons, and directly we look for the time of flight, and we get that blue curve, which is already the differential spectrum. And here you see, if you deconvolute nicely the molecular excitation and the dissociation and the ionization tail, we can describe in an unprecedented way inelastic scattering in hydrogen, or here in that case tritium. Now let's look to the size of the error bars of our recent one, which we published. We have a statistical error bar and a smaller, by a factor 2, systematic error bars, which is composed by all these points. I don't want to go in detail to it, but the blue bars are background features, and the orange one are source features. And now we try to improve the experiment from 1 to 1, and I show you 2 important instrumentations. One is that we let into the tritium source a huge amount of Krypton 83M, which is a metastable conversion electron emitter. So it's a source of monoenergetic electrons. We run a 10 gigabecquerel source to have enough count rate, because we are after about the sharpest line that conversion electron emitter does. That are the 2 N lines, and 1 and N2, very sharp lines where the line width is not really known. You see it's a rather step-like function, and the width is only determined by the magnetic field ratios. We do that to get the ultra-high precision by co-circulating krypton and tritium, and that we can do at 80 Kelvin. The second is about the background. I told you that from the first to the second run, reduced background, but the background is still a factor 20 higher than we anticipated. So what we then do, we realized what that background is. It's unfortunately what was our largest fear. It's coming from the volume, for a reason which we didn't know for a long time. And we shifted the analyzing plane, so that is the place where the highest retarding potential is, and the lowest magnetic field, downwards to the detector, to just make the volume smaller. And as you see here, we could reduce the background at equal features of the spectrometer by applying some smart calibration methods by a factor 2. And that are the runs which we are analyzing and hope publishing soon, and unfortunately I'm not allowed to tell you the results. We took much more data. This is since our start of data taking in early 2019 up to here. And we are now in run 9. We have just started run 9. Here you see the data up to run 8. And that are the two first results which limit the neutrino mass to 0.8. That are results which you see have much more statistics. And you see here these phases. We could happily run the experiment full time during COVID by taking all the measures, having two measurement teams who do not see each other to avoid the risk that the whole experiment stopped, and we survived running the experiment all time. Now I show you of a particular run where we have put in what we have so far. That is the latest run came in 5. And here you see our previous uncertainties, which we have the statistics. We have made the systematic so much smaller by the two measures which I mentioned, lowering the background by that shifted analysis plane, and which made all some other background things like some over dispersion because of stored particles, because of radon disappear. And we also controlled back the source-related systematics much better because of our high-intensity conversion electron campaigns by crypto. Now, if we take all the runs up to that came in 5 of 2022 into account, then we would get this sensitivity in statistics and systematic uncertainties. There is some background part because that is not all these data have this little background features. And what we would get is such a plane where we would expect our result, and the sensitivity you can read here is a little bit 0.45 electron volt. So another factor 2 in reduction of the sensitivity on the neutrino mass, which would come soon. And if you compare from what data, it would come from the data up to end of 2021, and we are running now in spring 2023, so we have much more data. What would that mean on the so-called Moore plot of neutrino mass sensitivity when the first experiment started at the end of the 40s? Here you see the mass sensitivity over time. You see it goes constantly down, but you see also that there are some deviations from the constantly. Always when a new method was involved or a new experiment, the slope is steeper, and that is where we should end up in some methods here. Of course, we want to go down a little bit further here. So that is our systematic and statistical sensitivity limit we aim for. Before we talk about how we go there, I just want to tell you, Katrin is not only a neutrino mass experiment. It's so much richer. It can look for additional neutrinos. Is there a fourth sterile neutrino? It could be an electron volt scale neutrinos explaining some anomalies other experiments have got hints for, or it could be some part of dark matter, warm dark matter. We are looking for a local overdensity of cosmic relic neutrinos. We can look for Lorentz invariance violation, and we can look for exotic weak interactions. Because nobody has done such a precise beta spectroscopy. I just start to tell you a little bit about the sterile neutrino searches. Let's start with the electron volt neutrinos. And what a fourth neutrino mass eigenstate would just produce a kink in the beta spectrum. We have to would enhance the neutrino mixing by a 4x4 matrix and add a fourth mass eigenstate and that sterile neutrino. Sterile means it will not couple to the W and Z boson. But it would show up by the mixing into the electron spectrum where you have a light neutrino branch, that dotted line, and this active one. Why do we do that? Because there are hints for that by reactor neutrinos, by the solar neutrino experiments calibration, which use germanium, and then there is the mini-boon and LSND anomaly. If you put that all together, they don't fully agree, but it's a good reason to search for. What you see here is that mixing angle of that sterile neutrino and the mass difference square, that are potential errors, is closed potential regions of evidence. Here you see that from the solar neutrinos, and here you see it from the reactor neutrinos, and here there is a hint of a recent experiment. What reactor experiments can investigate is this area, but what Katrin can do is this area. So it's complementary, and Katrin excludes this area here already. If we take the new data, which unfortunately I'm not allowed to show you, we would cover that whole evidence claimed by the neutrino 4 collaboration, and we would go deeper, and with all Katrin data we would explore that region in complementary to other experimental methods. Now KEV sterile neutrinos would make warm dark matter and are interesting for the reason that the so-called WIMP dark matter hasn't been found yet. And here that is the front page here of a recent CERN career. So it's interesting for the field. Again, we would see that in a king of the beta spectrum, and we have just published our first long beta scan deep into the spectrum, 1.5 kilovolt, that is 10% of the beta spectrum we scanned for that effect, and we could exclude unexplored region down to sinus squared theta mixing angles in the 10 to the minus 3 range. But that is not enough, because there are cosmological exclusions, so you want to go much, much deeper. Katrin can in principle statistically do, but we need another detector. And that is a detector upgrade which we will do end of 2025. We will upgrade it with a Tristan detector, which is a highly pixelized surface drift detector, which can do much higher rate and has a better energy resolution and a better DAC. And you see here a first prototype which works very well, and how that all goes here in. We would then deep dig into the mixing region versus the mass of the sterile neutrino. That is where Katrin would be statistically, it would go down deep into the 10 to the minus 7 and a bit in the 10 to the minus 8 range versus neutrino mass. And again, it's complementary to other searches like the Hunter experiment, which is a US collaboration with a different method. And we can look for this cosmic relic neutrinos. Of course, we are not sensitive to it. We can only constrain a potential overdensity. Here what is plotted is a natural neutrino spectrum with solar neutrinos, atmospheric neutrino, extraterrestrial astrophysical neutrinos, and so on. And that is a huge neutrino flux. That are the 356 neutrinos per cubic centimeter I told you. How do we would see them? We would see such a cosmic electron neutrino hitting on a tritium, doing inverse beta decay, giving us a helium-3 atom, an ion, I forgot the plus, and a monoenergetic electron above the endpoint. On a log scale, this is the beta spectrum in blue, and above the endpoint we would see such a peak. Unfortunately for molecular tritium, it's speared out, but we still can look to that. And what you see here is our constraint parameter of overdensity, which we constrain as function of a potential neutrino mass. And what you see here, that is our current value, and that is where we would end. We would constrain it at the order of 10 to the 10. That means we are not really sensitive to it, but we are more sensitive than anybody else. The problem is that these relic neutrinos have so much little cross-section that that would be not a strong signal. Now we would also like to go on in the next years with a more sensitive neutrino mass, and I told you we have one problem, is the background. And I showed you that plot, that every low energy electron born here is accelerated and counted to the detector. Where do they come from? We have so many sources of background which we all eliminated by magnetic fields, by electrostatic repulsion fields, by avoiding traps, so on and so forth. But there's one background we didn't expect. So radon is everywhere, to a little extent, also here in the room. And there's a little plate out of radon daughters on the wall. I see here colleagues from the dark matter experiment LC. They know, they have played out. Also our xenon experiment has that. But that is all beta-decay, alpha-decay, all charged particles which you can eliminate. But there could be that sputtering of a daughter of that lead decay of the polonium-210 sputters off atoms a lot. They are either ionized or neutral, we don't care. But in a few cases, it could be excited in a Rydberg state. That means you have an ionic core and one electron on a classical orbit around, and it takes little to ionize it. The whole spectrometer is at room temperature, so it provides a bath of infrared photons with a density of about 6 times 10 to the 8 photons per cubic centimeter. And that allows to ionize such an excited neutral atom which overcomes our electric and magnetic barriers. It ionizes it here, and then the electron runs to our detector. And that is very bad. We cannot distinguish them by energy with our present detector. We need bolometer detector of the next or super next generation. What to do? They are born with very little energy, K Boltzmann T, and run down the thing. So they have not large cyclotron energy. So they come at the detector with a little angular distribution compared to the signal electrons. So you just could differentiate that by angle. So you ask your particle physics colleagues, how do you do that? And if you tell them we have 18.6 kilo electron volt, very little energy and a strong magnetic field, they have no idea. What can you do? And that was the idea of Hamish Robertson from Seattle. He said, maybe we should do something on the cyclotron radius, because our electrons durate with a cyclotron radius of 100 micron. And the blue electrons have a small cyclotron radius, and the signal electrons in orange have a large cyclotron radius. And then we proposed at Munster a method where we built honeycomb-shaped detectors which are active on the side walls, and you see here in the computer simulation the signal electrons would hit the side walls, whereas the background electrons mostly go through. This is an electron microscope picture of something shaped out of a silicon detector, a silicon wafer. How to make a detector out of it? We are pursuing 2 different methods. One is to build our own microchannel plate. You know, a microchannel plate, if you have a hit on the side walls, it generates an electron cascade which you could accelerate to our present Katrin detector and count that. And the background electrons just go through and is counted as a single electron. That is one way which we follow up. And the more aggressive way is we take our silicon detector of Katrin, we bring it into the microstructuring lab by deep cryo-etching and make this honeycomb structure on top of the inside the detector and build such a detector which directly differentiates signal from background. You may count that as a crazy idea, but we checked with colleagues from high energy physics which etch holes in their detector just to make them even thinner. That is a recent finding. It could work. And we tried out, it worked. So what we do here in my group is at the moment we take little Hamamatsu pin diodes which we microstructure in the Munster nanofabrication facility. You see here on the optical microscope our honeycomb structure. We are getting better. We are solving that. We build a setup to test the angular response, and what you see here is a count rate above background versus detector angle, and you see it has this what we call the ATEF response, the angular transverse energy filter response, which we aim for Katrin. And it might well be, we are going on with the development, that the silicon ATEF, that's how we call it, is becoming a viable option to approach the final Katrin mass sensitivity by lowering the background and keeping most of the signal. I think I'm running a little bit out of time, but I just show you there are two different approaches to the neutrino mass in a direct experiment followed up. One is by the echo and by the Holmes collaboration. What they both do is they look not for a beta decay, but that on the isotope holmium-136 an electron is captured, which gives the excited state of atomically excited, so you have a hole in the electron shell of dysprosium and a neutrino which you can't measure, and that de-excitation of that hole of the dysprosium is what you measure. And that is a response what is here being measured in echo. You see the different atomic shell lines, and you see here the continuous spectrum underlying, and that end part of the spectrum is just a phase-space spectrum like the beta spectrum, and here the neutrino mass is buried. Of course, that goes with single bolometric detectors where you have to implant the holmium, and the two collaborations work differently, whereas Holmes works with test detectors, Echo works with magnetic microcalorimeters. And they are at the moment having developed a method to get large pixel arrays by frequency multiplexing. They have not really come up with very stringent results, but they are on their way. Another very interesting method developed by mainly US groups is the Project 8. Project 8 runs a tritium source in somewhat similar to Katrin. Molecular tritium inside a magnetic field, and they make use of the cyclotron motion. Again, Hamish Robinson involved, so he's very fan of the cyclotron motion. This cyclotron motion means, like in a synchrotron, the electrons is always accelerated and emits cyclotron radiation. If you can pick up that with antennas, you are sensitive to the kinetic energy of the electron because the frequency depends not only on the magnetic field, but also on the total energy, that means mass plus kinetic energy. And here is a reason, the first tritium cyclotron radiation emission spectroscopy CRESS event, where you see in time of a millisecond the frequency going down because the electron radiates by the beta formula energy, and sometimes you lose a lot of energy by an inelastic scattering. By that they reconstructed the tritium beta spectrum, which has only a few thousand events, and they come up with a result which limits the electron neutrino mass to 155 electron volts, so a factor 200 larger than the Katrin limit, of course, but they want to go for a staged approach to reach a 40 millielectron volt sensitivity. Let me summarize. I hope I could convince you that the direct neutrino mass search is very important, not only for astrophysics and cosmology, but also for particle and nuclear physics. And these searches are complementary to cosmological analysis and neutrinoless double beta decay searches. The direct neutrino mass experiment Katrin is taking data with unprecedented precision with this ultra-strong tritium source and high-resolution spectrometer, is continuously improving statistical and systematic uncertainties. I gave you a glimpse on some of the systematics and on our statistics, and is the first sub-electron volt sensitive experiment with a limit of 0.8 electron volt, and we will soon report on data with 0.5 electron volt sensitivity. Katrin measures the beta spectrum with unprecedented precision, and therefore we can allow other physics search channels beyond the standard model, electron volt and KV sterile neutrinos, CMB neutrinos, and so on and so forth. Katrin's background is dominated by Rydberg electrons, and also from outer ionizing states, something somewhat similar excitation. And the efforts to lower the background goals is at ATEV and terahertz radiation, of which I didn't talk about. And there are new direct neutrino mass projects, this electron capture experiments with bolometer, Project 8. And Katrin will go on. With the Tristan detector, we will search in 2026 and 27 for KV sterile neutrinos. and we are starting off a phase beyond that, what we call Katrin++, because we have a wonderful instrument, a wonderful instrumentation, and we haven't found so far the neutrino mass, and it's around. Maybe we have to go more than an order of magnitude, but we have a young generation who is devoted to go for it, and the older generation will support them. Thank you very much for your attention.
Okay, thanks very much for this very clear talk on an impressive project. Questions? Oh, Nina, I guess you each. Oh, sorry, I mean, oh, yeah, Lisa, sorry.
Yeah, okay. Too far back. So the latest results from cosmology, we had new results from the ACT collaboration this morning that claim, that claim an upper limit of 0.12 eV from CMB lensing. So if I understood correctly, you actually won't reach that sensitivity in the near future. Is that
No.
right?
So if we don't lower the background, if that ideas and methods I showed would not work, we would reach a sensitivity of a little bit below 0.3 electron volt. With our background improvement, we would be in the 0.2 electron volt region. So by saying the two numbers, they are not so much different, but cosmology measures the sum of the three neutrinos. If they are about the same, it's 0.12 divided by 3, it's 0.04. That is where project 8 wants to go. So what we aim for with Katrin++ is maybe even lower. And of course, that is not by far not trivial, but it's not completely hopeless.
One more question. So I mean, I am hopeful that with cosmology, combination of CMB lensing and spectroscopy, we'll have a real measurement in the next 5 years, say. If you have that answer, does it help you target your experiment in some way?
Yes,
obviously we want to check both.
Yeah, of course your current limits are really challenging. We don't know directly what to do. We have one idea is, so we have that integrating spectrometer. So we have about 40 steps where we switch the voltage. If we would exchange our detector into an array of cryobolometers with superb energy resolution, we would gain a factor 40 in time, and that would make a huge step. If we would have, instead of 2.6 electron volt energy resolution, really the edge what bolometers would produce in the future, we would get another factor. At the same time, we have improved all the other systematics that could bring us maybe in that reach where we would help. So my personal understanding is if cosmology goes on like that, it will be always ahead and will be a challenge for the direct mass search, and we would only be able to confirm unless there is something strange in nature and we come to different results.
Okay, let's see, Nina's next.
I had actually the same question about cosmology.
Okay,
so
that's it.
yeah.
Me too.
Oh,
It's of course every...
if you have the same.
Giorgio, I have one more
Okay.
question. Can you explain, because this is beautifully impressive experimental work, like the amount of, I mean, this is just, how on earth do you know that it's Rydberg electrons that give you the background? Can you say a bit more? I mean,
How do we know?
No, it's coming from Rydberg electrons. Like
Yeah.
plasma radioactive
Yeah,
decay.
I fully agree. It's such a crazy idea. When the first ideas came out, come on, we didn't believe that. So we did a couple of proof of principle experiments. So a Rydberg atom is an ionic core with an electron around, which you can easily ionize by that infrared radiation, but you can also field ionize it. So we have this double layer wire electrode outside. So we can increase the electric field strength. Every Rydberg electron passes through, and we can change our background rate according exactly what the Rydberg model would produce. The second proof is, okay, it's the alpha sputtering decay of a radon daughter. We could calibrate that by letting radon-222 in, but the half-life of lead-210 is 22 years. We stop measurement for the next 100 years. But there are 3 radon isotopes. We can use the other 2, which are having short-lived daughters. We injected, we saw an increase of our background, which just went away when we used the radon-220 source with a half-life of the lead-212, which is the corresponding. And we then used another radon source, the third radon, and it all agrees. We used radon-219 from a radium-223 source, and unfortunately it all coincides. What we do not directly distinguish, there could be also, there's a fraction of auto-ionizing states which make our pictures even worse. But unfortunately that is a proof, and next time we would do such an experiment by venting the whole spectrometer with radon-free air, like some of the underground experiments, but nobody in the world knows about this sputtering Rydberg atoms reason.
Okay, other questions? Yes.
If you're looking at the endpoint and looking for bumps for the cosmic neutrino background search, are you not also sensitive to neutrinoless double beta-decay at the endpoint? Like, why are those different signals?
In principle, if we would have an isotope which could go double beta-decay, then you would be right. But we don't have an isotope which is able to do that, because you would then tritium decay into a triple proton state which is not bound, and therefore you don't gain energy. But in principle you are right. If that would be an isotope which could do single beta decay and double beta decay, you would be right.
I have to ask, because the distinction between the cosmological measurements of the sum of the masses versus what you're measuring. Think about it. What is the mass you're measuring? So in the moment of the decay, it's in a pure electron neutrino state. So is this the weighted sum of the mixed mass eigenstates multiplied, weighted by the mixing?
Exactly. Very good. So let me go to that slide. Let's assume we would be having not Katrin plus plus plus, Katrin super plus plus. An experiment with super high energy resolution. In the decay, there's an electron neutrino born, and then the phase space gives us 3 beta decays, like when I showed the sterile neutrinos, 3 different kinks, and you would see the 3 mass eigenstates with their mixing angles. That would be the ultimate experiment. I learned today that you may do that with cosmology in some future as well, and that was astonished. I said that would be the smoking gun for the neutrino mass. Unless we can resolve the 3 mass eigenstate, we would see a coherent, incoherent superposition of all mass eigenstates contributing by these mixing angles to the electron neutrino mass. Because what we do is a projection on energy, and then we see the composition.
I had actually a question I want to ask you. So you said you moved the high voltage plane downstream to have less volume. So why did you build this? Why can you do that? I would imagine that the spectrometer is the size it has because that's what you need. Otherwise, you could have built a smaller spectrometer.
Yeah. Why we can do that? Because we have that wire electrode and these air coils where we can shift electric and magnetic planes. But it goes with a pain in the neck. Because that picture, what I showed you, is of course where do I have it? That is of course completely wrong. That is just to guide the eyes. Our analyzing plane is just such a shape. It has a parabolic shape, and we need, because we have these calibration tools now in hand, we can calibrate the electric and the potential and the magnetic field in this analyzing plane. And spectrum and use a Tristan detector to resolve in differential ways